Our project was making a herringbone steering rack system. To give some background, a steering rack system is a rack and pinion system where the steering wheel drives a pinion, which then pushes a rack, which then pushes on some linkages that orient the wheels of a car while driving. The reason why we are using a herringbone gear instead of a spur gear is that the helical teeth mesh better and therefore provide greater distribution of force and therefore reduce stress on the system.
Since we were simply making a prototype and not a working model, we did not use any metal or any metal machining processes. We simply used 3D printing and laser cutting to build our prototype, while also having some pre-assembly editing processes such as sanding and increasing tolerances.
Cockpit control forces document recommended steering systems to be designed around 100 to 145 newton meters. We chose 100 newton meters since that is still way more than a driver would exert in a typical driving condition. Functional dimensions were modeled after Bulls Racing's current Narco steering rack. In addition, the project was influenced by dissecting a steering rack made by Milterra. This came from USF Racing's F2013 race car. The Milterra rack as a design reference was good in that it helped us form a frame of reference. However, it created a problem because from what I observed in the design process is that it pulled away from a first principles design approach. Let me explain. A bolt-on race-ready part designed and fabricated before the semester ended would have been based on, first of all, the performance design parameters, and then manufacturability, and finally cost. The initial direction we chose took the form of the Milterra rack. This took a lot of design time. As a result, the only way we were able to pass 100 meters in the FEA was to use very expensive grade 5 titanium on the rack and the pinion. In addition, we found out later in the semester from Dr. Carey at the DFX lab that a herringbone gear pinion is very difficult to machine. Therefore, the Milterra steering rack was probably designed with different performance parameters than ours. I think a lesson to be learned here is that design references should be assumed to not match your specific design parameters. Anyways, by the time this was figured out, we had already spent a lot of time in the design process, and that pretty much killed our initial aspirations. However, we were able to demonstrate a lot of CAD skills, such as herringbone rack and pinion modeling from scratch, with a little help from the toolbox. This was a tremendous challenge to achieve meshing of the gears. We also used weldment profiles in the chassis and advanced mating techniques, such as the rack and pinion. And we used equations and link dimensions that kept the part files and the assembly slightly organized, and there are probably some more in here. Here was our list of parts and fasteners.
Through our work, we took on many hurdles, though none greater than the issue of figuring out the design of our double helical gear, which had a consistent issue of meshing with our rack. This issue was initially discovered with the use of the interaction detection tool, and through careful analysis, we were able to eventually solve the problem and complete the project. Though, unfortunately, with the completion of our project, we couldn't finish everything we wanted to. So in the future, if we were to do our project again, we would include defining achievable clearances and backlashes on double helical gear design for machining purposes, performing a GD&T test for machining services on the parts, having the use of better materials such as titanium for the gear and chromium for the rack, and performing a physical test using an actual car. Thank you.